Hello everyone, welcome back to this channel. Today's lesson, we are going to learn a very important concept in mathematics, which is called continuity of a function at a given point. By the end of this lesson, you will understand one, what continuity means, two, the conditions for continuity, then three, we look at examples of continuous and discontinuous functions. So let's dive into the first section of this video. Now, when we say continuous, what does it mean? A function is said to be continuous at a point if the graph has no breaks, no jump or hole at that point. So in simple words, you should be able to draw the graph around that point without lifting your pen. So when it's continuous, you can draw it smoothly without lifting your pen. All right. So these are some examples of continuous functions. So this is a polynomial function, this one here, and this is a rational function. We are saying that it is continuous for all values of x, and it is continuous for all x not equal to 0. So this is a rational function. So when x is 0, this changes to something else. It's going to be difficult to define it. And we have a trigonometric function here, and it's also continuous for all values of x. Now let's look at the examples of discontinuous functions. We have some here. Let's consider this piecewise function. From the left hand side, we have 1. Then the right hand side, we have 2. So since you can see that this is not equal to this from the left hand side, from the right hand side, the limits are not the same, then we say that it is not continuous. So the left limit equal to 1, the right limit equal to 2. The limit does not exist at 0, x equal to 0. All right, and we have a removable discontinuity hole. This is a This is a rational function. Now you can see that if you are to find the x value straight, right? If you are to find the function or the functional value straight, you can substitute in. Realize that what you are getting here, you get 0 divided by 0, which is going to be indeterminate, right? So the function is not defined at s equal to 1. But the limit do exist because you can simplify this one here. Now this difference of two squares, you can get x minus 1, x plus 1. Then x minus 1 will cancel out this. Then you have x plus 1. When substitute 1 in, you get 1 plus 1, you get 2. So the limit do exist, but the functional value that is not defined. And this is also another one. A function is not defined at x equal to 0. This is a rational. So when it happens, it's not defined. Mathematically, we say a function f of x is continuous at a if the limit of f of x as x approaches a is equal to f of a. That means that when they take the limit of that function as x approaches that point, then taking the functional value for that function, they should be the same. What it means is that if I have a function, if I have a function, then to check that it is continuous at a given point, let's say a, when I take the limit as x is approaching a, it should be equal to when I substitute a straight into the function. So when it equal, we say that what it is what continuous at that point a. But before this condition is true, three important things must happen. So let's dive into this important things that we are talking about. So we are going to look at three different conditions that we can use to determine whether a function is continuous or what discontinuous. All right. So conditions for continuity. First one, the function must be defined at the point. So if you have, let's say, you have a function f of x equal to x squared, you have x squared. Then, if I have 2, let's say it is the function, or at that point, it is at a point, what, 2. If I take the functional value, let's say I substitute 2 into this function here, and I get 4, then the function is defined at what? S equal to 2. You can see that we are getting a value, right? All right. So it should what? The function, that means that f of a must exist. F of a must exist. Now, 2, the limit must exist. The limit must exist. So when we say that a limit do exist, now the limit exists if we take the limit from the left hand side and from the right hand side. If they are the same, we say that the limit do exist. So the value of the function as x approaches a from the left and right side must be the same. They should be what? The same. So if I take the limit of that function when it's approaching that point from the left hand side, and I take the limit of that function when it's approaching that point from the right hand side, and they are the same, then the limit do exist. That's one condition. So if the two sides are different, then the limit does not exist. And we have the third condition. The limit must equal the function value, or it must be equal to what the functional what value. So the limit obtained must be equal to the actual value of the function. That is, if I take the limit of that function as x approaches that point, or as the value approaches that point, then taking the functional value, they should be what? The same. If this is true, then the function is continuous at that point. If it is not true, it's not continuous at what? That point. So we have three different conditions that we take note of. So the first one is that the function must be defined at the point. And the second one, the limit must exist. And we said that the limit must exist. For a limit to exist, the limit from the left-hand side and from the right-hand side should be what? The same. Then we have the last one, the limit must be equal to the functional value, right? Yes, that's the three conditions that we can use to determine whether a function is what? Continuous at a given point. Let's look at some examples of continuous function. Let's consider this function here, f of x equal to 2x squared plus 1 at x equal to 3. Now, let's use our conditions. Now, when we take f of 3, so the functional value is equal to what? When we substitute 3 into it straight, we are getting 19. Now, taking limit of that function as x approaches 3, the same value. So since the functional value is equal to the limit as x approaches the point 3 are the same, we can say that the function is continuous at the point s equal to what? 3, right? So this is simple. Now let's look at another example on discontinuous. So now let's consider the piecewise function. So this is a piecewise function. So a function, you see that it is defined in two or more different ways. All right. So in this case, we are looking at this at the point s equal to 0. Now we are saying that it should be 1 when x is less than 0. So from the left hand side we have 1. We have 1. Then from the right hand side we have what? 2. Now you can see that from the left hand side, from the right hand side, they are not the same. So since the limits are not the same, the function is not continuous at s equal to 0, right? So this is quite simple. So it is not continuous. It is not what? Continuous. Since the left hand side and the right hand side are not the same, it's not continuous. So the function is continuous at the point if. So this is to remember the rules or the conditions that must be satisfied to know that a function is what? Continuous. 1, the function exists at a point, and the 2, the limit exists, and the 3, the limit equals the function value. So these are things, conditions that you should note when you are checking for the continuity and the discontinuity of a function at a given what? Point. All right, so that's for today. All right. Once these three conditions are satisfied, the function is what? Continuous at that point. Thanks for watching. If you find this lesson helpful, don't forget to like, share, and subscribe to the channel for more mathematics tutorials. See you in the next video.